Hi, everybody. Mr. Haney, we're going to talk about types of radiation. We're going to go on to some new stuff. There's no test on the specific heat stuff. We'll do that later. Don't worry about it. We're going to talk about radiation because, I always wanted to be the Hulk. Let's see what it looks like. 1896, we had a French dude named Antoine-Henri Becquerel who discovered that uranium emits invisible rays accidentally, literally by accident. He had a big old chunk of uranium and he set it down on his desk next to a photographic plate and then left for lunch. And when he came back, because the plate was right up next to the rock, he picks up the rock to move it, and the plate behind the rock or under the rock, I forget which one it is, had developed. Well, that's weird because it was in the dark. There's no reason for the plate to have light shining on it. Back in the day, they actually used pieces of glass with chemicals treated on them instead of film because they hadn't invented film yet. So having this rock develops a piece of the film was a big deal. And he had two grad students named Marie and Pierre Curie who named this process radioactivity. They called the rays that they couldn't see radiation because it was radiating from an object. And together they isolated a whole bunch of different radioactive elements and won the Nobel Prize for Physics in 1903. Becquerel got the top billing for that because he was the full PhD. And the Curies were, they were graduate students, so they got credit because they worked on it, but they didn't get the money and they didn't get the medal. Okay? They did all the work. Becquerel took all the credit because he had the PhD. And they're like, all right, fine, you want to play like that? Fine, I see how it is. They finished their PhDs. They were both way smarter than he was. Okay? And Marie Curie went on to win several Nobel Prizes with her husband, Pierre, and Becquerel ended up working for them. So, if you know stuff, you can always be better than the people who are holding you down. Now, radioactive atoms go through a lot of weird, funky changes when they emit radiation. Radioisotopes are radioactive because their nuclei is unstable. Okay? They're so big in most cases that they just fall apart. But they fall apart in three distinct ways. And stability is determined by a ratio of protons to neutrons. Okay? Too many neutrons makes it unstable. So I don't know, when I was a kid, I broke one of my mom's coffee mugs. Go figure, my mom is a coffee addict like I am. But I broke one of her favorite mugs while washing it. Here, I'm doing the right thing. I'm washing the dishes, and the handle snaps off in my hand while I'm washing the mug. I'm like, oh, crap, she's going to kill me. So I do what every self-respecting teenager does when they know they're about to die. I went and got glue. Right? So I dried everything off as best I could. I made sure it was good and dry. And then I put some glue on the handle pieces and stuck it together, and I held it nice and tight, trying to make sure it would hold, held it like that for 10 minutes, trying to make sure I got a good solid hold. I let go, falls off. But I caught it. So I tried again. You ever try to use too much glue on something? And then the only thing the glue sticks to is itself? Yeah, that's kind of what happened here. The second time, I did not catch the handle, and it shattered into 1,000 pieces. So I'm like, all right, crap. Well, been nice knowing you, world. So my mom comes home from wherever she was off to, grocery store, I think. I said, Mom, I was doing the dishes, and while I was washing your mug, the handle snapped off. I tried to fix it, and then all I did was break it some more, and I'm sorry. She's like, oh, don't worry about it. I got plenty of other mugs. It's like, I was panicking for 2 hours over this. At least be upset. Parents, what can you do? So too many neutrons makes it unstable, just like too much glue means it doesn't stick to anything. Okay? An unstable nucleus loses energy by emitting radiation during radioactive decay. And this just happens all by itself. It's a spontaneous process. It's just like, you know what, fine, I can't handle this anymore, and pops away apart. There's 3 types of radiation. First one's alpha particles. Okay, this is basically, you're going to take this big atom and you're going to break off a tiny chunk that looks like a helium nucleus and shoot it out. Okay? You get 2 protons and 2 neutrons. That's the nucleus of a helium atom. So you're just going to take this little piece of the nucleus and throw it away. Kind of like I threw away all my fat clothes when I lost all the weight, and now I'm fat again. Yeah. Alpha particles written as either 4,2-He or as the Greek letter alpha, which Google will not let me do. Okay, which is kind of awkward. But the Greek letter alpha kind of looks like the Jesus fish. Okay. So the 4 on top, this right here, that's the mass, 2 protons, 2 neutrons. The 2 on the bottom is the number of protons. Okay? Uranium-238 gives off this radiation. Uranium-238 is kind of a big nasty. This is what we use in nuclear weapons and such. You take 2 protons away from this element, uranium-238, what do you get? Well, 92 minus 2, right here. 92 minus 2 is 90. That's thorium, element 90. 238 is the mass, minus 4 makes 234. So I get thorium-234. Okay? Again, the bottom number is the atomic number. The top number is the mass number. So the mass goes down by 4. The atomic number goes down by 2. Okay? Alpha particles don't travel real far or real fast because they're kind of fat compared to the other 2. So beta and gamma, they're big. They've got a positive charge, and as soon as they hit 2 electrons, they're looking for a balloon to fill because they're now just a helium atom. If it's outside your skin, paper or your skin, paper, skin, will easily stop it because it's a relatively big particle of radiation. Okay? The only problem alpha particles have is if they get past your skin, because your skin is fairly dense. But if you swallow it or it's injected into you, then it can penetrate the soft tissues that aren't as dense, and now it becomes a problem. My Uncle Roy had cancer. He had a cancer the size of a baseball around the ascending aorta from his right lung. Okay, and it was literally just kind of squeezing the aorta shut. Well, it's around a vein that's this thick. So if you operate, they couldn't operate, because if they nick this even a little tiny bit, okay, because it's coming straight from your heart and it's under a huge amount of pressure and it's this freaking big, he would bleed out in seconds. So what they did, and this is 15 years ago, something like that, they took this little tiny thing, looked like a sunflower seed, filled with an alpha emitter that was going to wear out in about 6 weeks. We'll talk about half-life tomorrow. And they, in the doctor's office, they make a little cut on his chest. You know, they gave him some little happy drugs first, but they make this little cut on his chest, and they push this little sunflower seed shaped thing into the tumor, stitch him up, send him home. So it's feeding radiation directly to the tumor, which is pretty cool. 6 weeks later, they come back. The tumor's about half the size it was. They're like, great, let's do it again. So they slice him open, pull the old one out, put a new one in, a little deeper, sew him back up, send him home. And they got it down from the size of a baseball to about the size of a walnut in the course of 2 or 3 treatments. I forget how many he had. That ain't bad. and it only irradiated the tumor. It didn't radiate or irradiate the lung or any of the surrounding tissue. It localized the radiation to just the piece that was actually causing the problem, which is really cool because you don't have all the other secondary tumors arise from it. It was very cool. Then we've got beta particles. Beta radiation basically happens when a neutron has a schizophrenic episode. It's like, I can't take this crap anymore, and breaks itself in half. You've got a neutron, and it turns into a proton and an electron. The proton stays in the nucleus. The electron, like a bullet from a gun, shot out of the nucleus. Okay? The beta particle is, let me see here. My annotate thing going. This right here, 0, -1 electron, or it's written as, I got it as a B there, capital B there, but it's actually like a B with a tail, like that. Okay? I don't know why, it just is. So here we go. This is what happens in a neutron right here. You've got 1, 0. 1 is the mass. 0 is the atomic number because it's not a proton. It's a neutron. So it has 0 for the bottom. That breaks apart and gives you a proton, hydrogen, and an electron. Carbon-14, radiocarbon dating is done with this stuff. Carbon-14 breaks down into nitrogen and an electron because, again, here I'm subtracting 1, right? I'm throwing away an electron. So 6 minus a -1 is 7. See, all these numbers here on this side have to add up to the numbers on this side. It's arithmetic, is all it is. 14 plus 0 is 14. 7 minus 1 is 6. You get nitrogen plus the electron. A piece of wood, like a 2x4, can stop this. A strip of aluminum foil can stop this. No big deal. Okay. Clear my drawings and go forward. And the last one is gamma. This is the one that made the Incredible Hulk. Okay. This is just an electromagnetic radiation. It has more energy than visible light. So it's beyond the visible light spectrum. It's beyond the X-ray spectrum. All right. So this is stronger than the X-rays you get at the doctor's office. And it's usually emitted along with alpha and beta particles. Okay. This is actually why uranium is so dangerous. It's not because of the alpha emission. It's because of the absolute crazy amount of gamma that's given off. Okay. Because gamma is just super high energy. And the symbol for gamma typically is this. It's like that Jesus fish standing on its head. But again, I can't find a way to do that in Google, so I just put a G there. Sorry. Okay. But again, it's given off in addition to the other two. So there's a couple of examples there, but it looks like just like the other stuff. It doesn't do anything to the nucleus at all. All right. It passes through the wood, through the human body, etc. You can stop this with a couple of meters of concrete or several centimeters of lead. So in the presidential bunker underneath the White House, you have both of those. You have about 6 to 8 feet of concrete and about 2 inches of lead surrounding the bunker so that there's no radiation getting in there at all. Okay. I forgot to mention that beta radiation is the kind they use when you're getting radiation treatments for cancer. If they're irradiating larger areas, they can't do the little tiny thing. They're having to do a bigger area. Beta radiation is what to do because it doesn't penetrate the entire body, but it does go in. It doesn't go all the way through, but it does go in. Okay? And that's it, folks. Just a little bit on the 3 types of radiation. And your homework is going to be doing some of these here. Some of these radiation equations. Nothing major. Okay? Answering some basic questions about radiation. All right? So, that's about it. So be good, and I'll talk to you later. Bye.